Welcome. This is ECE 341 Random Processes, Part 1, Lecture 13. In this lecture, we will finish our discussion from Chapter 3, although we will supplement it with a little bit of material from Chapter 7. I'd like to include discrete unconditional random variables, which just fit nicely with the Chapter 2 topics. This will allow us in our next chapter, or our next lecture, to be able to start Chapter 4, which is on continuous random variables. Much of what we're going to talk about in this particular lecture are related to concepts we've already seen before, so I've written most of it out beforehand just so we can go through it in a time-efficient manner. So what are we going to start out with? We've already discussed the idea of discrete random variables, and there's a lot of nice known discrete random variable families. We introduced some of those like the binomial or the geometric or the Pascal or the Poisson, but not there's not going to be any way that we can specify every possible random variable family that could ever be of interest. So the way we're going to oftentimes achieve our ability to model a wider class or a wider variety of random variables is by taking known distributions and then undergoing some sort of transformation on them. So we will take functions of known random variables to create new random variables, and we're going to spend our initial time talking about that. In the case of discrete random variables, then, our ability to describe and understand, so our ability to describe and understand discrete random variables is greatly enhanced if we can just look at functions of known random variables. That is, we're going to create a new random variable y that is a function of a known random variable x. Because we are currently looking at discrete random variables, it turns out this is a really easy thing to do. We basically take our new random variable y and we express it in terms of some function g of that known random variable x. This particular random variable y is also called a derived random variable because it's derived from that other random variable x. We know that a random variable, in this case y, can be understood or known if we understand or have its probability mass function. And it turns out the probability mass function for y is really easy to get for a discrete random variable. Essentially, all we do is we take a look at all those transformations of values x that map particular y's, right? And we add up their corresponding probability mass functions from x. So all of the values that map to a particular y, we take up the corresponding probabilities and we add them up, and that gives us the probability that random variable y equals that particular value, little y. Let me give a real simple example of this. Suppose we roll a fair five-sided die. Because it's fair, we know that any of the five outcomes, 1 through 5, right, have probability equal to 1/5, and we have 0 everywhere else. So you have a 20% chance of getting any one of the outcomes, 1, 2, 3, 4, or 5. I'm going to create a new random variable, a random variable y, that is going to be derived from this random variable x. And the mapping function I'm going to use in this particular case is that I'm going to let y be equal to 0 if x was an even roll, and I'll let y be equal to 1 if x was an odd roll. There is another way we could actually do this in a different kind of math, right? We could say something like y is equal to the mod, which is basically a remainder after division, right, of x with 2, something like that. So try a value of x equaling 2, for example. 2 divided by 2 has a remainder of 0, which is exactly what we expect. In fact, any even number that is divided by 2 will have a remainder equaling to 0, which is the mapping we needed. Any odd number that is divided by 2, its remainder is going to be 1. So just another way of expressing that same condition that I've written above. So in order to fully understand that random variable y, this derived random variable, we would like to get its probability mass function. That would be the most complete way to understand it. And we know that the probability mass function py of y is going to be based on any value of x that maps to a particular y. We just add up the corresponding values of the probabilities of x. So, for example, in this particular case, we know y can only take on two values. Y can be 1 or 0. Y equals 1 when what? When x is 1, 3, or 5, one of those odd rolls. That's what we said, 1 if x is odd. Well, if I sum up over x on all those values x that map to a particular value, y equaling 1, and we just take their corresponding probabilities, which in this case are all 1/5, I'm ending up adding 3 of those values 1/5 together, and that's going to give me a total of 3/5. For y equaling 0, it's the same kind of process. The probability mass function for y equaling 0 is going to be a summing over all values x that map to the value y equaling 0, which in this case is x equaling 2 and 4. We add up their corresponding probabilities, each 1/5, and so I'm going to get 2/5 out of that. Combine it all together and I can get this standard sort of representation for the probability mass function. PYY in this particular case is 2/5 for y equaling 0, 3/5 for y equaling 1, and just setting it 0 everywhere else. This probability mass function, like all probability mass functions, has to satisfy all the known kind of conditions and requirements for probability mass functions. We can see here that the probabilities are all greater than or equal to 0. We can see that across the range space, the probabilities sum to 1. We can also see here in this particular case, because multiple values x go to particular values of y, right? So you have multiple values of x going to a single value of y, that we're losing some information here. Knowing that a roll is odd or even doesn't tell you which odd or even value it was. So in this particular case, we lost some information about our original random variable. I highly recommend that you go ahead and you read the examples in the book. There are some really good examples in there, and they just take a few minutes to read through. So let's move on a little bit with this. Now that we know about derived random variables, we can also talk about expected value of derived random variables. There are some theorems on this in the book, and I encourage you to look at those and also take a look at some of the proofs. I'm going to, by and large, not prove these. So let's consider a derived random variable y being equal to some function or mapping of that random variable x, where x has a known probability mass function px of x. We certainly can talk about the expected value of y, right? Y is a random variable, and we know that it has an expected value, which can be gotten as summing over the range space of y and then taking y and weighting its probability mass function y. So that's just the normal definition of what expectation is. You take whatever you're expecting, y in this case, weight it by the probability mass function, and add up over all values of y. Turns out there's another way we can do it in this case of a derived random variable. We can also sum over all values in x because we know y's come from the x's, right? And we would add up what? Well, what is y in terms of x? We said y was equal to a function of x. So if I'm looking expected y, that's expected gx. And expected gx, you would, because that's just a function of x now, you would just take that function, multiply it by its probability mass function, px of x in this case, and sum over all values of x. They're exactly the same thing, just two different ways of getting it. This second method, right, this one that I'm going to box now kind of in red, is a really interesting idea on trying to find expected y. Why is it so different, and why is it sometimes really preferred versus other methods like the first one where you have it in the standard way? Well, this second form, if you started out knowing what the probability mass function of x was, and you knew that you were going to derive a new random variable y, but you were just a little on the lazy side and you didn't want to find the model for y, so you didn't want to go through all the effort of finding the probability mass function of y, you can still find this descriptive statistic, this expected y, without ever having to find py of y. You don't have to find y's probability mass function. You can completely do it in terms of the probability mass function of x. So that second form that's in there, okay, these kind of summary statistics, expected y, expected value of a derived random variable, can be gotten from the original random variables model. You don't have to find the derived random variables model. So if you're only interested in what was the average value of y, this is definitely a shortcut worth taking. It's worth considering taking anyway, because it will save you the work of having to find that probability mass function. There's some additional theorems and properties that we can talk about. We'll go ahead and go through these. These are all very easy to prove, so I'll leave most, again, the proofs to you, or you can ask during the recitation session if you'd like to go through any of these. So let's take a look at some of these. Let's let A and B be constants. Okay, so we're just going to have some constant values in there. What is the expected value of a constant? Well, you could use any random variable to do this. So expected value anything is the anything weighting a probability mass function and summed. Because A here doesn't depend on the random variable, it could be pulled out the sum, and I would get A times the sum of all those probability mass function values, which is just 1. So the expected value of A is just A. Well, that's not a surprise, right? What's the expected value of a constant? Just the constant, right? No particular surprise there. I can also look at the expectation of a sum of two different derived random variables, or two functions of random variables. Expectation for a discrete random variable just involves a sum, and summing is a linear operator. So this guy could be written as the expected value of gx, right, plus the expected value of hx, something along those lines. So you can get that expectation of a sum as the sum of expectations, something along those lines. This third property that we're going to look at is sort of a combination of the other two. Here we have a sum of two things, and so I know I should get out of this expected x, right? And then I'm going to have minus the expectation of that constant mu x, so that's just going to be minus mu of x. But what is expected x? That expected x is just mu x, and so in this particular case, I get mu x minus mu x is equal to 0. So the expected value of a random variable minus its mean is equal to 0. If I mean adjust a random variable, it becomes 0 mean. That's not a surprise either. The final one is just a generic linear transformation on random variable x. So I'm going to take x times a plus some offset b, and we can combine a lot of what we've just done, and it's no surprise that this ends up coming out as an a expected x. I can pull that a outside because it doesn't depend on the random variable itself. It's a constant, so it could be pulled outside of the sum. And then the expected value of a constant is just that constant b. So expected ax plus b is equal to a expected x plus just that constant b. Another little note just before we get on to the idea of variance and standard deviation. This is a thing that I occasionally see people make mistakes on. Suppose that you had something like a derived random variable y that was just equal to another random variable x squared, right? So I take whatever my random variable x is and I square it. I could look at something like the expected value of y, which if you just make the direct substitution, that's the expected value of x squared. I would note, right, that this is not equal. It is not equal to this idea of the expected value of x quantity squared, right? Those are totally different things. So you can't pull that squaring outside and make it like the mean value squared. Doesn't work that way. This is a kind of an important step or important thing to recognize as we move to the next thing, variance and standard deviation, because we're going to see to do variance and standard deviation, we have to be able to handle expected x squared, and we can't get it in this sort of cheap shortcut way of just taking the mean squared. It's just not the right kind of math. So let's talk variance and standard deviation. Variance really just provides an indication of a random variable's variability from its mean. And so we're going to define it here. We're going to define it as v of x. And just because it's such a common kind of quantity, it gets its own special letter here. So v of x stands for variance of x. But variance is really nothing more than an expectation. It is still an expectation. And we know what an expectation is. An expectation of something is the something weighting all the probability mass function values added up over everything in the range space. So it's an expectation. What's it an expectation of? We take our random variable minus its mean, right? So this is sort of the deviation from the mean, and we square it, right? We square it. Then make sure that we're adding up all the deviations, whether they're to the right side of the mean or to the left side of the mean. They all contribute to this kind of measure of variability. We'll also shorthand notice or provide a shorthand notation for this as being sigma x squared. So sigma x is, we're going to find out, called the standard deviation. The standard deviation squared is known as the variance. So sigma x squared is the same as vx, is the same as the expectation of the quantity x minus mu x quantity squared, something like that. Notice this expectation, so let me use a little bit different color here. Let me go ahead and make this green. This expectation, what are we taking an expectation of? And remember what expectations are. They're just like an average value, right? So we have some random variable minus its mean, and then we square it. Something squared is always positive. If I take the average value of a bunch of positive numbers, there's no way that that average can be negative. So an important kind of property associated with this variance is that the variance itself has to be a quantity that is non-negative. There's oftentimes that I'll see people go through a calculation and they mess the math up somewhere and they end up computing variance as being a negative number and they leave it and they don't say anything about it. That's definitely just a red flag throwing it in your face saying, hey, you did something wrong. Do not give us or do not believe a negative variance. It's just physically not possible. If you get a negative variance in your calculations, you absolutely did something wrong. You need to go back and recheck your work because it wasn't right. So let's think of another way we might go about computing out the variance. We know by definition the variance is equal to what? It's the expected value of the quantity x minus mu squared. So we're going to take that middle thing, that thing we're taking the expected value of, and we're going to just expand out x minus mu x squared. So if I expand that out, I get an x squared, right? I'm going to get a minus 2 mu x, and then I'm going to get a plus mu x squared. Expectation is a linear operator, so the expectation of a sum is the sum of the expectations. So I'm going to get an expected x squared, and then minus 2 mu x is a constant. It can be pulled outside the expectation, and I'm left with minus 2 mu x expected x. And we know expected x is just mu of x. And then the last one was expected value of mu x squared. That's expected value of the constant mu x squared. That's just mu x squared. So if I look at that middle term, minus 2 mu x times mu x, that's minus 2 mu x squared plus mu x is just going to give us a total of minus mu x squared. And we add that to the first term, expected x squared. So one way of computing out variance is by taking the expected value of a random variable squared minus the mean squared. That is another completely equivalent way of finding our variance. We can define our standard deviation. I'd already mentioned this before. The standard deviation, sigma x, is just the positive square root of the variance. So positive square root of sigma x squared. Variance is always positive. Taking that positive square root is always positive. Standard deviation is always reported as a non-negative quantity. Okay, something like that. There is a rule of thumb. This is a rule of thumb that we'll get more into detail later when we get to continuous random variables, but it's worth pointing out now because it kind of gives us a way of thinking about what variance means and being able to put it into some intuitive context. So I'm going to call this a rule of thumb. So we're going to be looking at a rule of thumb for variance or understanding variance, and we're going to do that through the standard deviation or the square root of variance. This is based on the normal distribution to be studied later. What's the rule of thumb? The probability, if you will, or the amount of values or the amount of a population that we expect to be within 2 standard deviations of the mean is about 95%. What's another way of saying that? The probability that a random variable x is within the mean minus 2 standard deviations to the mean plus 2 standard deviations should be about 95% of the population. Let me draw a distribution, even though it's not a discrete one. I'm just going to show a distribution of some sort. Suppose we have a random variable whose probability kind of looks like a bell shape like this. So I've got values on the horizontal x, and on the vertical here, you can think of that as being somehow related to probability, something like that. This is the classic bell curve, right? So there's all sorts of things, and that is, by the way, this idea of a normal distribution. This bell curve is kind of a form of a normal distribution, or a normal distribution is a form of a bell curve. So in this particular case, this is a unimodal, okay? So a single mode distribution. That distribution mode, because of its symmetry, is at mu x, okay? If I take that mu x minus 2 standard deviations, so if I come back here 1 and 2, so this is mu x minus 2 sigma x, and I stop there, right? And then I look on the other side and I say mu x plus 2 standard deviations, so 1, 2. So this is mu x, right? And I'll give myself a little space by erasing that x, mu x plus 2 sigma x, and I stop there. And I look at all the probability or all the likelihood that's in between in there. So all this probability in there, that should be 95% of the probability, right? So let's do another example of this. Suppose that you took an exam, right? And that you got a 50%. And so you're sitting there thinking, man, I'm in trouble. 50% isn't all that great. What am I going to do? We also said that probably you aren't going to be asking for the whole probability mass function or the distribution for that. But we could get a couple of these summary statistics, if you will. And the two most common ones are mean and variance. So let's go ahead in this particular case and just start writing it out. So your score, right? Your score maybe was x equaling 50%. And you wanted some idea to know, how well was this score. So you find out the distribution of this guy had a mean, right, being equal to something like 40%. You now know that you're 10% above average. Just knowing that mean definitely helps us out. Now, if I do something like this and I say the standard deviation was equal to 20, for example, something like that. What would that tell you? That would tell you that if I took the mean, 40%, and took plus or minus 2 standard deviations on either side. So 2 standard deviations, 2 times 20 would be 40. So that would say from 0% to 40 plus 40 is 80%. That's about 95% of the class in this particular case. So in that particular case, because you have a score of 50, which isn't even 1 standard deviation above the mean, that's probably in here somewhere, right? You know you're better than the mean, but you're not like greatly better than the mean, right? There's probably quite a few people who are above you. On the other hand, now, if you did something like the following, we said that, hey, what if the standard deviation was something like 5, as an example? Now, in that particular case, the whole situation changes, and it changes pretty dramatically. We can see that the mean, mu x equaling 40, plus 2 standard deviations, right? So if I look at mu x plus 2 sigma x, right, that is equal to 50, which is your score, right? So you're 2 standard deviations above the mean. That puts you right out here at this edge. That means that you know that there's a whole bunch of people behind you. If this symmetric distribution had 95%, right, that was in that kind of bulk area that's within 2 standard deviations of the mean, what does that tell us about these little probabilities out here? That's probably 2.5%, and you probably got 2.5% down there. Now, these are approximations. They don't work perfect for every single one of them, but in this particular case, if we were looking at a standard deviation equaling to 5, given your score of 50 and a mean of 40, you would expect that maybe only 2.5% of your classmates were above you, something along those lines. So these two summary statistics, mean and variance, can tell you kind of a lot of information. They can tell you some really useful information about a discrete random variable. Again, that rule of thumb best holds for symmetric unimodal distributions where the peak is at the mean. There are a few properties and theorems involving variance. Again, these are straightforward to prove, and we'll just go ahead and go about doing it. What's the variance of A? Well, remember what variance is. Variance is the expected value, right, of whatever it is, minus its mean. Well, what's the mean of A? What's the expected value of A? That's A. Take that quantity squared. So that's the expected value of 0 squared, or the expected value of 0. Clearly, the expected value of 0 is just 0. So in this particular case, the variance of a constant is equal to 0. And that makes some sense, right? A constant is constant. It doesn't vary at all, right? So we wouldn't expect it to have any kind of variance that was greater than 0. The variance of x plus some shift, what is that? Well, we're adding some amount of value x, but remember what variance does. Variance, right, does something in its definition. It says subtract off the mean of the random variable, right? Subtract off the mean of this guy. So if I'm taking something like an x plus b, something along those lines, an x plus a constant, that x plus b's mean is going to be mu x plus b. And when I subtract that from x plus b, I'm just going to get variance of x. So in this particular case, I would expect it to be variance of x. You could call this guy like y, right? And that y has a mean mu y equaling to mu x plus b. Those are all from things that we had seen before. So this variance of x plus b is like the variance of what? Y, which we could think of as being the expectation of what is y. Well, we could call that x plus b minus its mean. That's mu x plus b again, but that's a quantity there, something like that. So the b's are going to cancel, and there's a squared in there, which is equal to the expectation of, we have like x minus mu x quantity squared, which is just the definition of the variance of x, something like that. So I've made a big mess out of this. I'm going to go ahead and erase part of this work. Just shifting by a constant doesn't make a bit of difference to the variance. And the basic reason why is because the variance mean adjusts everything. It's a mean adjusted second moment is another way of thinking about it. It's the expected value of something squared, but it's involving whatever it is minus its mean. And if you add a constant to something, you've changed its mean by that constant. And if you subtract the mean, well, then that's no longer a part of it. So this guy is just variance of x. How about variance of a constant times x? Because variance is the expected value of something squared, we're going to have the expected value of ax, that whole quantity squared. That's going to be an a squared x squared, right? And so that a is going to get squared in there. That not being a function of the sum variable can be pulled out. So we're going to get like an a squared variance of x, something along those lines. Again, the proofs of these, I'm justifying them in a more intuitive way right now, but the proofs aren't hard. You can definitely go through just like I did in the previous one before I erased it, and you can easily demonstrate these guys as well. So variance of a scaled random variable, something scaled by a constant, is just that constant squared times its variance, right? So if I scale a random variable by 2, I change its variance by 4, something along those lines. Now, if I combine those operations, I scale and shift. The shift again doesn't matter, and I'm again just going to end up in this particular case being able to get an a squared bx again, because that shift, that plus b, doesn't matter at all because variance is a mean adjusted quantity, something along those lines. Okay, so let's go ahead and move on. The means and variances of various random variable families are given in the text and in Appendix A. In one of our previous lectures, when we just talked about the idea of averages and we introduced the idea of expected value of x or the mean of x, I did write down all the means for all the different families. I'm not going to do that here. You can certainly look those guys up. They're in the textbook. They're also in Appendix A, which summarizes all the important discrete random variable families. So I'll let you take a look at those. If you need to deal with something like the variance of one of those known random variable families, just open up the appendix and grab that already derived value. You can, of course, like on the next test, you know that you'll be able to use a formula sheet. If you would like to have access to some of these distributions and their means and their variances, you should write down their PMFs. You should write down their means and variances and get that on your formula sheet. Let's still go ahead and go through the nitty gritty, show at least that the math here does end up working on this. Let's go ahead and show what the variance and mean, both, of a Poisson distribution is. One of our last lectures, when we talked about averages, we went and we proved a couple means. And one of the ones that I did not prove, I said it was in the book, was the Poisson. Well, part of the reason I didn't do that is because I knew I was going to do it here. So you're going to still get the proof for the Poisson, both its mean and its variance. So let's go ahead and do that. Recall that a Poisson has a probability mass function that looks like an alpha to the x e to the minus alpha over x factorial over the range space, x equaling 0, 1, 2, 3, all the way out to infinity. It's 0 otherwise, something along those lines. So I guess if I was going to be really complete here, right, I'd go 0 otherwise, something like those. That's the complete distribution that completely describes this Poisson process, and I would like to find its summary statistics. If you can remember back to the last lecture where I introduced the means for all the different families, you might remember that the Poisson had a mean, e of x, equaling to the Poisson parameter alpha. And so that's where we're trying to get here. I'll just show quickly how that can be gotten. Remember what a mean is. We sum over the range space of whatever we're taking the expectation of, in this case, x, right? And then we do what? We multiply it by the probability mass function, in this case, alpha to the x, e to the minus alpha over x factorial. Now I'm just going to do some manipulation on this and get it into the form that I want. Because I know, because I read Appendix A, that the expected value for a Poisson random variable is alpha, I'm going to pull out an alpha. So I pull out that alpha, and that means that the alpha to the x that I had before is going to have an alpha to the minus 1 in there, because alpha times alpha to the minus 1 is just going to be leaving that final alpha x in the inside. So I haven't changed anything. I pull out an alpha, I leave in an alpha to the minus 1, basically. There's still that e to the minus alpha in there, and I can sit there and I think about that overall x that I had. I'm going to cancel it with one of the x's in that x factorial, and that just leaves me an x minus 1 factorial, something along those lines. The only other little detail in here is that previously, when we started here, we started at x equaling 0, but at x equaling 0, we see that we multiplied by x, so 0 times anything is just 0. That term didn't contribute anything, so it's really okay that I go ahead and start at x equaling 1. All right, so now I've got a little bit modified form. I'm going to make a variable substitution, x prime equals x minus 1, put that in there, and I'm going to get alpha, and then I'm going to have a sum on x prime now, and that's going to go from 0 to infinity because of the shift up here that I did. And I'm going to have alpha to the x prime, e to the minus alpha over x prime factorial. Well, that stuff on the inside of the sum is just a Poisson PMF, and I know that the sum over the range space, right, of a PMF must sum to 1. So I'm going to get alpha times 1, and that means that my expected value is what I expected. It's going to be alpha, something along those lines. I next want to go ahead and do a similar kind of process in trying to find this variance. probably not so easy just to leave it in the V form. Let's get it in the form where we know mathematically what the operations are. So variance is just expected value of the quantity, right? X minus mu x squared. And what I'm going to do is I'm going to use a slightly different form, which we had derived second, which is the expected value of x squared minus the mean squared. I'd already computed the mean as alpha, so minus mu x squared is going to be minus alpha squared. For me to be able to finish this out and find the variance, I just need to find that expected x squared. So let's work with expected x squared. What is expected x squared? You take whatever you're expecting, right? That's the x squared. You multiply it by the probability mass function and you sum over the range space, something along those lines. I know that the x equaling 0 term in this sum doesn't contribute anything, so I don't have to worry about it. I can start that sum from 1, something along those lines. I do have this x sitting over here squared. I can take one of those x's and divide with one of the x's in the x factorial, and that's going to leave me one x in top because it was x squared before. One of them's getting thrown down to the bottom, and instead of x factorial, I'm going to have x minus 1 factorial, and I'm going to leave the other two terms alone, something along those lines. If I let this x minus 1 go to x, and I'm going to just let it go to x, I'm not going to use an x prime here just to simplify some of our combinations later. So I'm going to go ahead and make x minus 1 go to x. It's still a substitution. You could go through a prime if you wanted. What do we get? Well, now once I've made that substitution, instead of x minus 1 factorial, I'm going to have x factorial, right? And instead of alpha to the x, I'm going to end up needing an alpha to the x plus 1. And so I'm going to have a way of writing that as alpha to the x times an alpha there. I still have my e to the minus alpha. I'll leave that alone. And then I had x, but if I was taking x minus 1 going to x, that means x goes to x plus 1. So I can have an x plus 1 over here, something like that. And then the sum limits, because x minus 1 went to x, if x was equal to 1, right, 1 minus 1 is 0, so my new limits are going to go 0 to infinity, something like that. If you prefer putting this with a prime, you certainly could do that. That's just the way I chose to do it in this case. All right, so now I do what? I'm going to go ahead and take this guy, and I have x, right, times a bunch of something. I've also got 1, whoops, let's get that in the right color here. We'll see if I can redo that. We also have in here 1 times, that something in there. So I've got a sum of a sum, and I can break that up into two sums, right? The red sum, if you will, and the green sum, something along those lines. So if I go ahead and take a look at the red sum, that's the first one I'm going to show here. They all have this alpha here, so I'm going to pull that alpha out. I have a sum going from 0 to infinity. That one with the red had an x times all that stuff, so I'm going to have x times all of that stuff. Then the other one, the green sum, if you want to talk about that, it had an alpha as well, which I pulled out front. I'm still summing over 0 to infinity, so that's no problem. It lacked that x. It was just 1 times that something, so we had that something over there. Well, that something over there is just a probability mass function. That's a Poisson random variable taken over its range space. So we're summing up a Poisson. We know that sums to 1, and it's getting multiplied by alpha. That's how I get this alpha times 1. This other one, what is that? That is the definition of the expected value of a Poisson random variable x. That's something we already just derived. We know that that evaluates to alpha, but we'd also pulled an alpha out front, so I'm going to get alpha times alpha. What do I get out of all of this? Alpha squared plus alpha. I'm going to plug that in here to get my variance calculation. So I'm going to get an alpha squared plus alpha minus the mean squared, so minus an alpha squared. The alpha squareds cancel, and I'm left with just alpha. That's the variance of a Poisson distribution. Poisson's kind of neat, right? It's got a variance and a mean that are the same dang parameter. So mean of a Poisson is alpha, and its variance is also alpha. Let's go ahead and conclude our chapter 2 with a little bit from chapter 7. So this is kind of a weird way to conclude chapter 2, but I like including this chapter 7 stuff into chapter 2 because it's all material we've seen before, and it just helps us complete our understanding of discrete random variables. There's no reason to really delay it. I do encourage you to just also, as you're reading through, skip ahead, look at chapter 7, and just pull out those parts where it talks about conditional distributions, but for the ones that are discrete. And really, it's pretty intuitive, so it should go pretty quick. So we are going to conclude chapter 2 with a little bit from chapter 7, all on this idea of a conditional probability mass function. Here's the basic idea. I can have a random variable x, and I can condition it on some event b. That event b changes our information about x, and that becomes now kind of, you can think of that as almost like a derived random variable. It's going to be a new random variable with its own distribution. That means it has its own probability mass function. That probability mass function is going to be, by definition, called a conditional probability mass function. It is how is probability distributed for this random variable x when we condition on some event b having occurred. It really is nothing more than the probability that x equals x given b. It's a conditional probability, and we studied those before. So really, we don't have to wait to get this. We don't have to make this harder than it needs to be. It's easy stuff. We'll do a couple of theorem type stuff, and we'll interspace those theorems. We can get by on this pretty quick. We're going to interspace those theorems with a couple of examples as well. So suppose we have an event space BI where I goes from 1 to m. What was an event space again? It's just a set of mutually exclusive events, B1, B2, B3, all the way out to Bm, that partition our sample space, right? So it covers the entire universe of things that we're interested in. We know, and we had seen this before, we knew that if we had an event space B, right, that probability of x given bi times probability summed up gives me my probability of x. And so we can just put this in terms of the probability mass functions that are the conditional ones if we like. I can get the non-conditional probability mass function from conditional ones as long as we have an event space and we sum up over all the pieces that make up our overall universe. Let's quickly show this. This shouldn't be a surprise, right? If the B's cover everything that could be in the universe, right? If I condition on, let's just say there were two. Suppose there was a B1 and a B2. So B1 was one thing, B2 was all the other cases. If I look at the conditional probability mass function, P of x given B1, right? That means B1 happened, and we want to get all the probabilities there, and we weighted by how likely is B1. What is left? Well, if it wasn't B1, it could only have been B2. So we would want to include then, if we wanted to get the whole probability, right? We'd want to get all those probability B2s or probabilities related to conditioning on B2 weighted by their respective likelihoods. I think it's an example would help. You can also go back to our earlier chapters where we were talking about conditional probabilities, and this is related to expressions and relationships we've already seen. Just put in terms now of this conditional probability mass function. Let's think about an experiment or an example where people are taking a test and you either pass it or you fail it. Okay, so really we're interested primarily here whether you pass or fail something. And I'm gonna say that the distribution of scores, depending on whether you're passing or failing, are going to be defined in separate ways. So let's let a passing score be 59 up through 100. And we're going to assume the score on the exam is an integer value. That way we can make a nice discrete random variable. So passing scores are 59 to 100. That's pretty close to the standard 60 plus, but this instructor decided to be a little bit allowing a curve of 1%. So 59 to 100 is going to be a passing score in this particular one. And it's just the integer values 59 through 100. And what you might notice in there that there's 42 values in that, right? 59 all the way up to 100 inclusive. There's 42 values in that. And we're going to say that those passing scores are uniformly distributed. They're each equally likely, something along those lines. We're also going to say that the fail probabilities are uniformly distributed. And so that U out front is just our way of saying it's uniformly distributed, right? So our failing score distribution is also going to be uniform, but it's going to be uniform over these different range of values, a score of 1 through 59. This instructor's double nice because he never gives a score of 0, even if there wasn't a test done. So he always gives at least one credit or one point of credit just for having your name in the class roster. Okay, so what would we get in that? If you look at 1 through 59, but we're not including 59, that's why I'm using a curly bracket here. There's how many values in there? Well, there's going to be 58 values in there. Now all of a sudden this should make sense. If I take all the values from 1 to 100 inclusive, that should be 100 values. And I know there's 42 in one group and 58 in the other group. 42 and 58 is 100. That's the total number of scores that were possible as long as scores had to be an integer value. So passing scores have to be uniform and failing scores have to be uniform. We're going to throw in a little bit of additional information. We're going to say 40% of the people in general on this test fail, something along those lines. So I would like to know the PMF of an overall score. Think about this passing scores. That's scores conditioned on being in the passing range. What is the failing scores? That's the conditional, right? That's the conditional distribution, right? Assuming that you failed. And if we go back up to here, now we have an event space that is 2 in length, right? our BIs, if you want to call it that, B1 and B2. B1 would be your passing, B2 would be your failing, something like that. So what is my overall distribution? It's going to be a sum over two things. It's going to be the conditional distribution conditioned on you passing, right? That's this first one. Times the probability of passing, which is going to be 60%, the complement of the 40% fail rate. And then we're going to add to that the failure distribution, which is uniform again, right? Weighted by its probability, in this case, 40%. So we can go ahead and work on the math on that just a little bit. I'll go ahead and put in the numbers in this case. We know that if you have something in the pass rate, right? How many values were there? There were 42, and we said it was uniform on that. The probability for 42 things uniformly taken, right, is going to be 1 over 42. So I have 1 over 42 is the conditional probability mass function over that interval, right? And it's going to get weighted by the conditional or by the probability of passing, which we said was 1 minus 40% or 60%. So I need to take that particular one and we're going to multiply it by 0.6. If you go ahead and do that, we're going to find out that the pass probability in that pass range, 59 to 100, is 1 over 70. I can do the same sort of thing for the failures, right? There were 58 values in the failure rate, 1 through 59. We said they were uniform over that. If you have 58 things and they're all equally likely, their individual probabilities is 1 over 58. We're going to multiply that the probability of failing, which is 0.4% or 0.4 or 40%. And if you do that multiplication, you end up getting 1 out of 145. So we can see that a pass probability, right, is about twice as likely as a fail probability, even though they're both uniform over their respective intervals, and it would be 0 otherwise. I've gone ahead and sketched this a little bit. We see a uniform distribution over the fail rate, and we see a uniform distribution over the pass rate, but they have different weights, right? They have different weights. The first one, the fail one that we have in there, we already computed that out as being 1 over 145. So this first one is 1 over 145. And the second one, the pass one, we computed as 1 over 70. Now, if you add all of these guys up, what should you get? You should get a value of 1. And certainly you can show that. You know how many things there are in here. There are 42 of those guys. If you take 42 times 1 over 70 plus, and there's 58 in the other one, 58 times 1 over 145. If you do that calculation, you do get 1. And so it adheres to all the things that we need a probability mass function to do, right? It is non-negative probabilities that sum equal to 1. And just a reminder, if I conditioned, right, the conditional distributions in this particular case, like conditioning on us being a failure, it's just uniform over that failure rate. The condition on passing, uniform on that. The combined distribution here is not uniform, right? It's kind of like a hybrid of two uniforms, each with their own different heights, something along those lines. We're getting pretty close to the end here. Let's see if we can see this to the end. When an event B is contained in the range space of X, we see there's two possibilities. Either X can be a part of B or X is not a part of B, something along those lines. If X is an element of B, then what do I know? The random variable X taking on a value X intersected with B is just X equaling X. If X is not an element of B, X taking on a value X intersected with B is the empty set. Think about that. If I look at X not being a part of B, what's the chance that I get that X and B together? Well, it's not part of B. They aren't overlapping. It has to be nothing. If X is known to be a part of B, the chance that I get value X and B is just whatever that value X's likelihood is, something along those lines. How are we going to use this? It gives us an alternate way, basically, of understanding conditional probability mass functions. The conditional probability mass function, and we know this because of the way we defined conditional random variables. A conditional random variable, X given B, is X intersect B over B, something like that, right? So this conditional probability mass function is the probability that X equals X and that we have B over the probability of B. But we can look at the cases of whether X is a part of B or not. If X is a part of B, X equaling little x intersected with B is just X equaling X, and the probability of that is the probability mass function, Px of X. And we would divide that then by PB. If X is not an element of B, that top part, right, X equaling X intersected with B is the empty set. The probability of an empty set is 0. Divide by whatever, it doesn't matter, it's still going to be 0. So here's how we might think about a conditional probability mass function. A conditional probability mass function follows the general shape of our original distribution where it can happen, right? Where X is part of that thing we're conditioning on, because we conditioned on it. Because we conditioned on B happening, right? We only know that we're somewhere in B's range, right? So it has to follow the basic distribution of X. It has to look the same basic shape, right? But we're only doing that over where X is actually consistent with or aligned with or overlapping with the B's. If we conditioned on B and we looked outside of B, well, because we conditioned on B, we know that that couldn't have happened. So that has to be forced to zero. Because we're possibly getting rid of some stuff, because of this X not an element of B, we cut away the stuff that couldn't happen based on what we're conditioning on, right? This Px of X by itself would no longer sum to 1 unless we scale by the overall probability of B. Let's look at just a super ultra simple example on this. Let's go ahead and look at the probability mass function for rolling a four-sided die. I have 1, 2, 3, 4. 1, 2, 3, 4. I know these are each 25% likely, so I'm going to put 0.25 on that. So that's the PMF, right? That's the Px of X for a four-sided die. If I wanted something like this, if I wanted the probability of X given, right, that X was greater than or equal to 3 as a function of X, what would I get that looking like? That says that wherever X is part of the thing we are conditioning on, what are we conditioning on? X being greater than or equal to 3, X being greater than or equal to 3. It says what? It says that you want to go ahead and keep the original distribution shape, so 0.25. But I'm going to divide by the probability of B. What's the probability that X is greater than or equal to 3? I can do that off here on the side. Probability that X is greater than or equal to 3 is the probability X is 3 or 4. Each of them have 25%. That's going to be a half. So I'm going to take these values 1/4 and we're going to divide it by a half. That gives us 1/4 over a half is going to be 2 over a fourth, or 2 over 4, which is a half. So for those parts where X is a part of B, 3 and 4, we are going to have the scaled probability as 1/4 over a half or 1/2. So I'm going to get 1/2 here and I'm going to get 1/2 here. It looks the same shape. It's still like uniform over that interval. It just got scaled in probability. So everything got a little bit bigger in compensation for what? In those parts that couldn't happen, we're conditioning on B. We're conditioning on X is greater than or equal to 3. That means those roll values of 1 and 2 couldn't happen. We forced them to be 0 because of this stuff, right? So what do? We keep the stuff that we're conditioned on, part of B, right? And we end up doing what? We get rid of the stuff that is not an element of B. And because we are getting rid of probability, the other stuff has to get bigger, right? We have to get that guy bigger so that it still sums to 1. When you condition on some event, the underlying probability mass function shape doesn't change, right? You're only getting rid of values and then scaling everything that's left so it sums to 1. So let's go ahead and continue the example that we had just been working on. We were talking about exams that we're going to go from 1 to 100 just as integer values. Any kind of exam score from 1 to 58 was considered a failure, and we knew that that was 40% likelihood across all different exam scores. 59 to 100 were considered passing, and we knew that that was 60% of the scores. Suppose you knew your exam score was greater than 50. You emailed the professor and you said, "Can you tell me anything about the exam?" And he says, "Well, I've got most of it graded, but not all of it. I can tell you you're greater than a 50." Okay. Well, what would that tell you about parts of your exam score? Could we model this conditional probability mass function? Could we get something like, what's my probability of passing conditioned on this event of my score being greater than 50? Well, what's first off the probability that X is greater than 50? Well, we have all 42 passing values, which were each likely 1/70th. And we have 8 non-passing values, that's 50 through 58, each with probability 1 over 145. If you multiply those through, add them up, and simplify, you get 19 over 29, or a little more than 65% of the overall. So this probability that a score X is greater than 50 is a little more than 60%. That actually shouldn't be a surprise. We're including all the passing scores, and that was 60% of the stuff, right? We're including a few of the fails, but not most of them, right? Failures were 40%, and not most of them should be, no, certainly less than 10%, something like that. So 65 seems at least plausible to me. What is the conditional probability mass function, P of x, given that your score was greater than 50? Well, I look at those scores that are part of that x greater than 50. That's this stuff, right? And we are going to do what? We're going to take whatever was px. It was 1 over 70 for 59 to 100. It was 1 over 145 for anything less than 59, something along those lines. And then we just divide by the likelihood of our event, in this case, x greater than 50. We just computed that as 1929s. So I divide by 1929s and I divide by 1929s. Both of those are part of this condition x greater than 50. I keep the same relative kind of shape, the same relative heights between the pass and non-passes, right? But we scale them up so that they will sum to 1. If you do that math, you get 29 over 1330 for the passing values, and you get 1 over 95 for the fail values. This relative weight between those guys, the passing scores are still about twice as likely as the other ones sitting in there, something like that. Okay, so what can I? Let me see if I got that right. Yeah, they should both be at that same sort of ratio. They have that same relative height that we had seen before. So now we might do something like this. We might say, well, what's the probability that I pass knowing that I have an x greater than 50? If you had no knowledge of this, if I had no given something, you would just say, what's my pass probability based on the full statistics of x? And we already know that's 60%. If you know your score is greater than 50, there's still a chance of failure, but it's not as big as before because you know you don't have that scores 1 through 49. So I can use my conditional probability mass function. I can use that P of x conditioned on x being greater than 50, and I can just say how many of those values are greater than or equal to 59. Well, I could count all the scores 59 to 100 and use those probabilities there, or I could take the complement, 1 minus how many scores are in that fail side. Well, there's just 8 of them, 50 through 58, right? And they each have weight 1/95th. And if I do that, I end up getting 91.58%. So if you knew your score was greater than 50, your chance then of actually having passed the test would have been 91.6 roughly percent, right? Rather than the overall just 60% if you didn't know anything. Conditional probability mass functions, we're very close to being done, are like any other probability mass function. They have to be non-negative. They have to sum to 1. They have to have all those normal probability mass function kinds of characteristics and behaviors. A couple very quick final notes. If I look at the expected value of x given b, we can call that mu x given b. These are conditional means, if you will. We just sum up over all the x that are part of the thing we're conditioning on because we know b happened. That's why we said we conditioned on b. We are taking an expectation of x, so it's going to be x weighted by what? Well, instead of the regular probability mass function, you put the conditional in there. So it's just like you would expect. A conditional mean, right, is still a mean. It just uses the conditional distribution. And it's only summed over those parts that can happen when you have condition b, something along those lines. The very last one, and we will do a tiny proof for this and then we'll be done, is can we get expected x maybe using some conditional expectations? Here's the theorem. It says something like this. If I've got an event space of a bunch of events, bi, I going 1 through m, just like we had before, the expected value of x can be gotten from all these conditional expectations. Expected x given bi times their relative probabilities, p sub bi, summed over all those things that make up that event space, something along those lines. If this seems a little weird, if you aren't fully sure of where this came from or how it might be true, the proof really isn't all that bad. We've skipped a lot of proofs in here because most of them are easy. Let me show you that this proof also is easy. It's not something that's terribly difficult to do. And before I do that, let me maybe just make the statement of why we want to do this. Sometimes, right? Sometimes, I'd say sometimes this is hard to do, right? Sometimes just doing the basic expectation is hard. And sometimes, right, sometimes these are easy or given already. So if I have an easier way or something that has already been given as information, and I can use that to more easily get something that's harder to calculate, why not do it? That's certainly one motivation for this. All right, so let's prove this guy. We're trying to figure out what is expected x. What is expected x by definition? I sum over the range space of x times p of x, right? What did we see earlier in this lecture, though, is px of x in terms of some event space bi, right? We knew that that was a sum, I equaling 1 to m, of px given bi times the relative likelihood of bi, so probability bi. I'm going to interchange my sums, the sum order. So this sum is going to go over here. This sum is going to go over here. So I'm going to have a sum on I going from 1 to m. And then I can include anything that's a function of I, but not of x. There's only one thing that fits that. That's at PBI. So I can pull that one out. And then I'm left with this sum over Sx, right? And everything else which has an x in it. So that's going to be x p of x given vi. Well, what's a sum over the range space x of x times the conditional probabilities? That's just expected x given vi, right? Something along those lines. And then I'm multiplying that by probability vi and summing 1 to m. That's exactly what we had up here. And so we're done with that. Next time, chapter 4, we're going to do continuous random variables. My guess is that you'll like this quite a bit. There are a few quirks. We're going to have to work a little bit just to get a kind of a little bit different idea about how we express probabilities. It's a little different in there. But instead of dealing with sums, we're going to be mostly dealing with integrals. And for the most part, most students and instructors, for that matter, just have more comfort and familiarity working with integrals rather than sums. So a lot of the calculations will actually become quicker. That'll happen next time.